This video is going to help you to fine-tune your definitions of colligative properties. To begin with, a colligative property is one that, first of all, it's a physical property, and it's one that is only affected by the number of particles that you dissolve into a solution, not on the identity of those particles. And so colligative properties are affected when you raise the number of solute particles that are dissolved in the solvent. It applies to non-volatile solutes only, and a non-volatile solution is one where evaporation at the surface tends not to happen very quickly. So water is considered a non-volatile solute, and we can think of this solvent as water in the upcoming slides. An example of a volatile solute would be alcohol. It's evaporates really easily, and so the particles at the surface of the alcohol are escaping into the atmosphere fairly easily. There are three types of colligative properties that we'll look at. One is called vapor pressure lowering. The next one is boiling point elevation, and those are two are very closely tied. And then the third one is freezing point lowering. And we see examples of particularly boiling point elevation and freezing point lowering frequently, especially here in Minnesota, where we have to worry about icy sidewalks. You'll see how that comes into play here in just a moment. So vapor pressure lowering. This happens when you add solute particles to a pure solvent to form a solution. So here is the pure solvent, and vapor pressure is the pressure that the particles above the solution create on the surface of the solution. So notice that the container is closed in this Erlenmeyer flask, and at the surface there are constantly a few vapor or solvent particles that have enough kinetic energy to escape into the atmosphere. And once they escape, some of those particles get close to the surface of the solution again. And as their kinetic energy decreases, the attractive forces of the particles at the surface will attract those and bring them back into solution. When we introduce solute particles, let's say salt, and the salt dissolves. So what we see here are sodium and chloride ions that are in a solution. Notice that at the surface, those solute particles get in the way. So there are fewer solvent particles that are available to evaporate into the atmosphere. So there would be fewer solvent particles in the atmosphere, creating pressure on the surface, thereby lowering the vapor pressure. To understand boiling point elevation, we need to understand what happens during the boiling process. So as we add heat, let's say to a container or beaker of water, the kinetic energy inside the solution starts to increase. As soon as, let's take a look at the inside of one of these bubbles. As soon as the particles in the solvent get enough kinetic energy to break away from the liquid, they form gas particles within the solution. So there are some particles inside the solution that are getting enough kinetic energy to break away from the solvent and form this little bubble within the solvent to make a gas bubble. However, at the same time, atmospheric pressure is pushing down on the surface. And so if the atmospheric pressure is greater than the vapor pressure that's trying to form inside these bubbles, that atmospheric pressure will collapse the bubble. So boiling happens when the vapor pressure inside the bubbles or inside the solution is great enough to overcome the atmospheric pressure pushing down, trying to collapse the bubbles. What I've done is introduced some solute particles. They're not moving like the rest of the particles, but you get the picture. When there are solute particles in the solution, again, they get in the way and interfere with the particles in the solution that are trying to escape into that vapor stage within those gas bubbles. So the boiling point of a solution is always higher than the boiling point of the pure solvent. More kinetic energy means more heat, and so the water is hotter when it comes to a boil. Normally, boiling point at atmospheric pressure is 100 degrees Celsius for water. But if we add a solute to the water, in order for those bubbles to form at the boiling point, we have to add more kinetic energy. So the water actually is able to get hotter when we add the solute. The boiling point of a solution is always higher than the boiling point of a pure solid. We see an example of boiling point elevation when we add salt to our pasta water. The salt doesn't cause the water to boil faster, but it does increase the temperature at which the water boils. So when we throw our pasta in, the pasta will cook faster because the water temperature is higher. With freezing point depression, it also depends on this idea that the solute particles are getting in the way. So we've got the liquid particles here that are moving around, have kinetic energy. When they slow down enough, the force of attraction can overcome that kinetic energy, and the particles form the crystal solid, and they form the regular crystal lattice that we see in ice. When we add salt, let's say at the surface of ice, for example, what's happening with the ice is that at the surface, there are constantly particles that are getting enough energy to escape from the ice to go into the liquid form as the sun, let's say, beats down on the ice particles. And so at the surface of the ice, there are constantly particles of liquid. And so we throw salt on the surface of the ice, and in that really thin liquid layer at the surface of the ice, the solute particles are getting in the way of the water slowing down enough to reform ice crystals. And so even more kinetic energy has to be removed in order for the particles to become attracted to other water molecules in the ice form. We're going to see in a future lesson that we can actually calculate the amount of particles that need to interfere to either increase the boiling point or lower the freezing point. Another example is adding antifreeze to your radiator. It causes the boiling point to be increased, and it also causes the freezing point to be lowered. So it protects your radiator in the winter and the summer.